Welcome to this explainer. Today, we're diving straight into a document that, honestly, fundamentally altered the entire trajectory of artificial intelligence. I'm talking about the legendary 2017 Google Brain paper titled, "Attention is All You Need." If you've ever wondered what's under the hood of those incredible leaps in modern AI we're seeing right now, well, the blueprint starts exactly here. This paper completely revolutionized the field of sequence modeling by introducing a brand new, stunningly elegant architecture that they called the transformer.
Okay, let's quickly look at our roadmap for today. We'll start with 1, the sequential bottleneck, move into 2, the attention breakthrough, then look at 3, inside the transformer, break down 4, the power of self-attention, and finish up with 5, shattering translation records.
All right, kicking things off with part 1, the sequential bottleneck.
To really appreciate what the transformer achieved, we kind of have to understand the massive brick wall researchers were hitting back in 2017 with recurrent neural networks. As you can see, recurrent models process text step by step. It's exactly how a human reads, right? Left to right. But because you literally cannot compute word 10 until you've fully processed word 9, you inherently limit parallelization. This sequential constraint was causing major training bottlenecks, especially as sentences got longer. Plus, their memory of those early words fades as the distance grows. But look at the transformer model approach here. By ditching recurrence completely and relying entirely on a mechanism called attention, the whole process suddenly becomes highly parallelizable.
Now, the math straight from the paper's table 1 proves exactly why this was such a game changer. Just focus your eyes on that sequential operations column right there in the middle. For recurrent layers, the minimum number of sequential operations scales with n, which is just the length of the sequence. So it takes O of n operations. But for self-attention, it drops all the way down to O of 1. That means it requires a constant number of operations, absolutely regardless of how long the sentence is. It's an incredible leap in computing efficiency that fundamentally changed how we train these models.
Moving right along to part 2, the attention breakthrough. So how exactly do we bypass that sequential bottleneck? Well, the paper describes attention beautifully. They call it a way of allowing modeling of dependencies without regard to their distance in the input or output sequences. Think about it like this. Instead of reading a really long sentence word by word and, struggling to remember how the very first word relates to the 20th word, attention allows the model to just look at all the words simultaneously. It figures out which words are connected to each other no matter how far apart they sit in the text. The maximum path length between those long-range dependencies effectively shrinks to a constant, making it infinitely easier for the model to actually learn the context.
Let's crack this thing open. Part 3, inside the transformer.
Okay, I know. This diagram looks a bit complex and super intimidating at first glance, but I promise you it's primarily just 2 main structural blocks. On the left side there in the gray box, we have the encoder stack, and on the right side, the decoder stack. The author stacked 6 identical layers for the encoder and 6 identical layers for the decoder. The encoder's job is to take the input, say an English sentence, and map it into continuous mathematical representations. Then, the decoder on the right takes that mapped information and autoregressively generates the output sequence, like a translated French sentence, just one element at a time.
But wait, there is a pretty glaring missing piece here. If the model isn't reading sequentially left to right anymore, how on earth does it know the order of the words? I mean, if it processes everything at the exact same time, the sentence, "the dog bit the man," looks mathematically identical to "the man bit the dog." To solve this, the authors brought in positional encoding. Since they completely dropped recurrence, they add sine and cosine functions of different frequencies directly into the input embeddings. It basically acts like injecting mathematical timestamps. This gives the model the crucial information it needs about where each token sits, so it never loses the structural meaning of the sentence.
Which brings us to part 4, the power of self-attention.
Let's see how this all builds into something so powerful. The raw calculation here is a basic core mechanism, scale.product attention, which you can see on the left. But the authors quickly found that doing this single function with full dimensionality just wasn't enough to capture really complex language nuances. So what did they do? They created multi-head attention on the right. They literally take that attention mechanism, linearly project the queries, keys, and values, and run it 8 times in parallel. They call these 8 parallel layers heads.
Let's decode how these heads actually think, in plain English, because it's super cool. The inputs are transformed into 3 distinct vectors: queries, keys, and values. Conceptually, it's a lot like a database search. The query is what you're currently looking for, the key is the label or index in that database, and the value is the actual content. The model computes the dot product of the query with all the keys to figure out which words are most compatible or relevant to each other. They then scale this math down by the square root of the dimensions, which is a really vital step actually to prevent the gradients from getting too tiny during training. And here's why those 8 parallel heads matter so much. It allows the model to jointly attend to information from completely different representation subspaces. If it only had a single head, averaging all this data together would actually inhibit the model's ability to learn complex, multi-layered sentence structures.
And finally, Part 5, Shattering Translation Records. So what happened when they actually put this architecture to the test? 28.4. That is the record-breaking BLUE score the big transformer model achieved on the highly competitive WMT 2014 English to German translation task. Now, in the world of machine translation, the BLUE score is the rigorous gold standard. It measures output quality against actual human translation. The transformer didn't just casually beat the existing state-of-the-art results, it improved over them. And we're talking about beating massive ensembles of multiple models working together by more than 2 full BLUE points. It established a completely new ceiling for translation quality.
But the hits just kept coming. Look at this number, 3.5. On the English to French translation task, the model established a brand new single-model state-of-the-art score after training for only 3.5 days. And it did this using just 8 GPUs. To put that into perspective, this was a tiny fraction, literally less than 1/4, of the computational training costs compared to the previous best models out there. It decisively proved that dropping recurrence for pure parallel attention wasn't just highly accurate, it was a massive leap forward in training efficiency.
Which leaves us with a truly provocative thought to end our explainer on today. In their conclusion back in 2017, the Google Brain team noted that they were incredibly excited about the future of attention-based models, and they actually plan to apply them beyond just text. It really begs the question, if attention is all you need for language translation, what happens when we apply this parallel architecture to vast, complex inputs like images, audio, and video? The transformer removed the bottleneck of sequential reading, forever opening the floodgates for the massive, multimodal AI systems we are seeing scale up today. Thank you so much for joining me on this explainer. I really hope this helps structure your understanding of the transformer, and hey, keep questioning what's next.